In this video, we'll continue looking at amplifier circuits. So for this circuit, this is a summing amplifier, and it's the same arrangement as an inverting amplifier. However, we've got multiple inputs in this case. In terms of defining or calculating the transfer function of this circuit, it's exactly the same principle as the inverting amplifier, except now we've got multiple currents going on the input side. So we can say we've got a current here, IA, a current here, IB, a current here, IC. All these currents add together. Nothing goes through the op-amp. All the current goes through this way, through R2. So the current through resistor A is given by VA over RA. Similarly for resistance B and resistance C. So the three currents add up and all pass through the feedback resistor with this value. If we set all the resistors equal to 1 or one value, which we'll call R1, then we've got the same weights or the same scaling on each of the input voltages. So what we have is an addition of the voltages, and then this addition is amplified by the resistor ratio R2 over R1. And because it's an inverting amplifier arrangement, we have the negative sign there. So that's our summing amplifier, and it's a way we can add voltages together and then possibly amplify them as well if we want. In this circuit, we have replaced the input resistance with a capacitor. So we put a capacitor in here. The current going through a capacitor, as we said in the first video, is related to the rate of change of voltage across that capacitor. So I equals C dV in by dt. So our current in here, I, is given by this term. And again, it's an inverting amplifier arrangement. No current goes through the op-amp, so all the current, no current goes through the op-amp, so all the current goes through the feedback resistor. So the current through there will be minus V out over R. And again, we can equate the two together and say this term is equal to this term. We can rearrange, and therefore our output voltage is proportional to the rate of change of the input voltage, and therefore it's a differentiating amplifier. Always be careful using differentiation because it does amplify the noise, so that's just something to bear in mind. If we now switch these components around, so we have the resistor as the input and the capacitor in the feedback loop, then the input current is our voltage drop over our resistance, Vn over R, and the current going through the feedback loop is the rate of change of voltage times by our capacitance, dV out by dt times C. So again, the current coming in equals the current in the feedback loop. So this term equals this term. We can rearrange, and if we rearrange, we have dV out equals a function. So what we then do is integrate that over a certain time period. So we have dV out equals minus 1 over RC times V in. So what we need to do is integrate both these sides. When we find the integral, we will get this equation here. So our output voltage is summing up the input voltage over time and again scaling it by a function of our resistor and capacitor values. Our final circuit we'll look at in this video is what's called the difference amplifier or the differential amplifier. And in this scenario, we've actually got two input voltages, and what it's going to do is amplify the difference between these two input voltages. Now, if you remember back to when we originally talked about the op-amp and we said we put two input voltages in, it amplified the difference, but the amplification was so large, then it essentially saturated the output. Because we've now got this arrangement with feedback, we can control this gain a lot better. So the analysis of this is a little bit more complicated. So what we'll do is we'll label, if I can, label this point V pos, and we will label this point here V neg. So this has got a potential on it, a value of V pos, and this has got a potential on it with a value of V neg. Okay, so the first thing we do is look at the V pos aspect. And if you notice, this is similar arrangement to our non-inverting amplifier, where we have a potential, essentially a potential divider. We have a current going through here, nothing goes through the op-amp, and it goes down to ground here. So we can work out this current. So it's the potential drop across here, which is V2 times by our total resistance. And then knowing that current, we've got a resistance here, so we know this potential drop V pos is going to be that current I times resistance R2. So we can combine that together, and we say V pos is going to be a fraction of this voltage V2 defined by the values of the resistors. On the inverting input, we've got a similar arrangement to the inverting amplifier, where we're looking at the current going through here. So again, I'll just tidy this up a bit. So we have this as V neg at this point. We've got a current through here. So the potential drop across here is V1 minus V neg over R1. And that's our current I. And that current now goes through here. And the potential drop across here is V neg minus V out over R2. So because all the current goes through there, this term equals that term, which is what we have there. There's a slight mistake in my notes, so this should be actually negative, but it all cancels out, so it's okay. So we have the current flowing through this feedback loop is given by this value here. So these two terms equal each other, so we can equate them two terms. Say them currents is equal, and therefore we get this relationship on that side of the circuit. Now from Golden Rule 1, we have said that the op-amp tries to make these two voltages the same. So V pos and V neg will be the same value because the op-amp is trying to make it the same value. So our V neg here and here is going to be the same value as V pos, which we've defined as here. So we can substitute this equation into here and here, and we get it substituted in here and here, and therefore the expression then becomes this, which looks a little bit messy. But if we tidy it up, rearrange it, we eventually get to the transfer function. So the output voltage of this circuit is the difference in the input voltages, V2 minus V1, multiplied by our resistor ratio. R2 over R1. So we've got a gain, we've got a controllable gain term there, and it's amplifying the difference between the input voltages. So up to now we've considered op-amp circuits, but we've considered all amps to operate perfectly. So in the next video we'll actually consider what the real limitation of op-amps are, and then considering that we'll then move on to how we design to account for this.